welcome to the Signal Path. In this episode, we're going to do a teardown and analysis of a very interesting instrument, particularly an Advantest Wavelength Meter. Now, this is a unique instrument and most people don't really come across because it uses free space optics inside. And you have to be working in this type of field in order to get to see one of these guys. So I'm very excited to show you what it looks like on the inside. I'm also going to explain the principle of operation and how this equipment actually does what it does. It can measure the wavelength of any light source that you put into it, anywhere from 600 nanometer to about 1600 nanometers. So it covers just at where red is all the way into deep infrared. It's used for optical telecommunication. But I'm also going to show you some of the electronics that's inside, and then we're going to do a little experiment and measure a particular laser that is in the infrared region. We're going to put it in, do some measurements versus temperature. So let's take this apart, get started, and see what it looks like. So the front of the instrument is simple enough. This is a relatively old equipment, so it doesn't have a big fancy LCD display. But here it has some 7-segment display panel that shows you the wavelength or the frequency or other relative information. There's a little optical power sensor built into here so that it can tell you that whether you have sufficient optical power into the instrument in order to be able to make accurate measurements. So if the needle is on the green, then your measurement is good. It also has a GPIB port, so it has some LEDs and lights and the address select for the GPIB. But the rest of the button is really simple. It only does one thing. It measures wavelength. And so it can measure the wavelength of a coherent source like a laser, or perhaps the wavelength of an LED source that's not so monochromatic, it's not so pure, so you lose some resolution when you select the LED. But it also has a built-in self-test. If you do a master reset, it does its own calibration. You can average things out, you can do some chopping. So it really is very simple on the outside. You put in a fiber in here, which you can unscrew, and then put the fiber in there, and then you can measure the wavelength. But really what is interesting is what's on the inside. So I've already taken the 4 screws at the top that hold the cover. So I'm going to try and remove this cover. It's not as easy as it seems. There we go. And voila. So the first thing you see is that the main portion, the main center of the instrument is covered with another enclosure that's coated black. But on the left side here, on my left side, you can see there are some different kinds of cards in here. There's three modules that have been plugged in, and these different modules do different things. I'm going to take them out so we can see them. But let's get started with the main optical part. So I'm going to remove the screws for this optical component, and so we can take this cap off and see what it looks like. But before we take any of this apart, I want to give you a disclaimer. You should never open optical instruments unless you know what you're doing, for 2 reasons. First, there is visible and invisible optical radiation, like lasers that can come out of instruments when you open them, that can be harmful to your eyes, and especially if they are non-visible, because you can't even tell that you're damaging your eyes. The second is that every optical instrument like that, free space optics, have been very carefully tuned. If you open these up and move them or bang them around, then you're going to take them out of calibration. So you have to be very careful when you deal with this type of equipment. So this guy has only 4 screws. That's very easy to open. So bear with me while I do this. There we go. And you can see that this thing has been designed so that it can be easily taken apart, because it even has little handles here that you push, and then they rotate out and you get 2 little handles which you can grab and open. So I'm going to carefully remove this to see what is inside, which is really quite amazing. So what does this instrument do? Well, as I said before, it measures wavelength, but it measures wavelength using a very particular type of physics. It uses a Michelson interferometer inside. So this is a Michelson interferometer. So he was trying to measure Earth's ether early in the 20th century, I believe, which then the experiment ended up proving that there was no such thing. But out of that came his version of the interferometer. So the way it works is like that. So you have a coherent light source, like a laser, that starts from here. We can see that. The coherent light source is shining on a half silvered mirror. So it bounces against the mirror, goes this way, bounces against the mirror again, comes back down, and goes to the detector. But there is a second path. The second path goes right through the mirror, because the mirror is only half silver, so it's half transparent, goes through here, hits the second mirror, comes back, and bounces back to the detector. So both of these paths end up reaching the detector. But because this is a coherent light source and monochromatic, these two, when they combine on the detector, create fringing patterns due to destructive and constructive interference of light, because the wavelength, depending on the distance in here, that creates different type of fringing. So you can imagine if I change the distance between one of these mirrors with respect to the other mirror, I can change the fringing pattern, because it's the time that it takes, the distance or the time that it takes for the light to go back this way and this way with respect to each other, that defines the fringing pattern. So if I were to be moving this mirror back and forth, and I didn't know what the wavelength of this light source was, if I had a proper detector, I could measure the fringing pattern, and if I know the distance, if this is fixed and I know this distance, then I can measure the wavelength, which is exactly how this instrument works. It moves a mirror back and forth, and by shining this light through two mirrors, it can then measure the wavelength, because it has multiple detectors and it can measure the fringing pattern. This is a very simple explanation of how a Michelson interferometer actually works. But this instrument does all of that using free space optics. So let me zoom into here a little bit so you can see. So the light, this is the input of the circuit right here. So the fiber comes from the front of the circuit. That's the fiber input. The fiber input goes through a fiber that's all the way winding on the inside, but it ends up here. This is essentially the input. So this point fiber is connected to the fiber in the front. That goes through this little module in the front, this guy right here, and this module then takes the light fiber and defocuses it so that you can get a larger ring. Comes out of this node. Instead of a mirror, it uses two prisms that are back to back. So this light goes through this prism, bounces against this mirror, goes back through the prism, and shines on the sensor, which is all the way over there. The other path, the light goes through the prism, bounces against this mirror, comes back through the prism, and goes back again to the sensor. So because this thing can measure such a wide range of wavelengths, there's actually a mirror in here. So this guy can rotate. It can either stay in this way, where the light goes right through, or it can be in this position, where there is a mirror, and the light will bounce against the mirror and go to a different detector. So there's actually multiple detectors. I'll give you a close-up view of all of this, but just so you have a bird's eye view right now. So light comes in here, bounces against this mirror, goes through the detector, or goes through, bounces this mirror, comes back here, goes through the detector. And the fringing pattern can then be measured on the different type of sensors that you have. So here is the deep infrared sensor. The light goes this way for the deep infrared sensor, it goes that way for the near visible red colors. But this mirror moves like this with this motor. So this mirror can move back and forth, which then allows you to adjust this distance precisely in order to control the fringing pattern, which is then a function of wavelength. So let me turn this thing on. Okay, I'm going to do my best to hold this thing steady. So you can see all the components. I'm going to turn this thing on. Here we go. So as I told you, it has a motorized mirror that's continuously moving back and forth. And this movement, using the Michelson interferometer, will allow us to measure any wavelength that we want. But this instrument does something else. If I turn this light off, you can see, if you look closely at where the detectors are, that there is some red light already there. So there is some laser already present there. That's because this thing has a built-in helium neon laser that it uses as a reference. So where does that light come from? Well, if you look carefully, you can see that there is another mirror here. That mirror has light coming from underneath it. So light comes from underneath, bounces against the mirror, and goes to the prism. If I hold my screwdriver in front of it, you can see the light that is coming out of the laser right there. So this light from this laser, oh, it's complaining because I blocked the light. So this light comes through here, bounces against this, goes through the prism, goes through this combination of mirrors. So from here, bouncing all around and going all over to the sensor that it uses as a reference. So that laser is actually mounted on the opposite side of the instrument. So I'm going to open the opposite side of the instrument so you can see that. So if you think about it, the instrument always knows the position of this mirror because it uses a stepper motor, so it can always tell where the mirror actually is. So by measuring correlation between the position of the mirror and the detector on the sensor there, it can find the wavelength. So let me turn it around and open the other side so you can see the laser itself. Okay, so here's the back of the unit. So I just flipped the whole thing upside down. Again, you can see there is another chamber, a cage here that is painted black. And remember, this thing is painted with a non-reflective paint both on the inside and on the outside, so that the light doesn't bounce around and any stray light is caught and does not reflect back onto the sensors to throw off the measurements. So similarly, this thing has 4 screws. So I'm going to open that. And this one as well. This is the fiber from the input that is sitting on top of this. I'm going to have to move that on this side. There we go. And another last screw. Alright. Carefully remove this. And here it is. And here's the back of the unit. So this is the stepper motor that turns, that moves the mirror. This is a high voltage power supply that powers the helium neon laser. And here's the helium neon laser itself. So the helium neon laser generates light that comes out of this end. There's a mirror, it bounces against a mirror there. Right there. Bounces against this mirror, bounces against this mirror, comes out of this little hole, bounces against this mirror, goes right through the board, down, comes out of the other side. If I can flip this, this thing is very heavy because of all the free space optics in it. Rotate that. There we go. There it is. And the light comes out of this. That's the same thing on the other side, goes to the mirror, bounces around, and so on, and it does what it does. So let's go back to the back side again so we can look at some of the electronics. So there is a motherboard at the back of this where all the cards are plugged in. I want you to appreciate the construction of this instrument because there's obviously a lot of thought has gone into it. So the entire optics is mounted on this heavy steel platform where everything's tied down, and so that it doesn't vibrate and doesn't shake, so it doesn't throw off the measurements, because a nickel interferometer requires very, very stable optics. Now you don't find these type of instruments very often because again they're extremely expensive to make and they can break very easily. But so here's the motherboard at the back. You can see it, it is I think probably a 4-layer board which has a connector that goes to the front panel that controls all the buttons and the display in the front, and it has its own little AC motherboard here, so all the 110 volt or 220 volt voltages come through here, and then they go through the power supply which is buried at the back. So this thing that sticks out in here is actually the power supply. So let me remove the camera, get a better idea. So there in the back, right behind that grating thing over there, is the power supply. So the cables go through the power supply, come back out, and then they power with these. I've measured these voltages as plus and minus 12 volts, which powers this entire motherboard where all the cards are plugged in. So this was, if I can find some date on it, there it is, there's a date right there. You can see it, 1985. So this was manufactured in 1985. And I'm going to turn it around from the other side. I'm going to take some of the cards out so you can take a look at it. There's a lot of mistakes, a lot of bot jobs where people have wired things that have been mistaken. This must have been an early early module. But let me give you a quick view of what this looks like. Here's a helium neon laser, goes through the mirrors. There's the first mirror, there's a second mirror, goes through here, goes through the board. Here's the high voltage power supply. When the power from the power supply this guy comes directly from the power supply in the back of the unit. Here's a high voltage connector that connects to the helium neon laser, which requires, I believe, something around more than 1000 volts in order to work. So let me look on the other side. So let's take a closer look at the boards that are on here. So we have the detector boards. So in here you can see actually on the PCB there is a symbol of a diode, and that diode is one of the detectors. You can see that the output of the photodiode goes through a two-stage amplifier here before it is collected by this wire, which then goes through this cable assembly through this connector here, which then reaches one of the boards that processes the data. But underneath it is another board. So the top board is for visible light, and the bottom board is for the infrared light. And if you look closely here, you can see already a little change they have made there with that resistor. So you can see someone had gone there and made a little modification that must have been a mistake on the board. So there are a lot of these on this design. So here's this little board here. Performs a few functions. One function is that the power for this board, all these wires that you see here that power the detectors and the sensors, they run around this mirror, they come through here, and they reach this board. So this board has, from this bunch of cables here, it connects to the power supply and to the motherboard. So all the power comes through these cables. So these cables power the detectors, as well as the stepper motor, which is the motor in here that is used to rotate to push the mirror back and forth, the stepper motor here. So this little, you can see that there's classic signs of a stepper motor driver there. It has capacitors, diodes, and transistors to switch different coils inside the stepper motor to turn this mirror, and also the other stepper motor driver, which is this one down here. So if you look at 3 boards here, from the last time that I opened this, the board at the very top, which is connected to this cable, that cable connects to this connector back there, which is a GPIB connector. So the last board is the processing board plus the GPIB, a lot of digital stuff on it. The second board is the synthesizer board, the middle one, which then connects to this board, which collects all the data from the sensors and gets the signal from the synthesizer, from the VCO, the PLL from the other board. So let me take those out so we can take a look at them. Okay, so let's start with the analog board from the detectors. Carefully unplug these cables. Everything is nicely labeled on the cards themselves, so it kind of reminds me of Agilent design, where everything is carefully done so that it's not only easy to repair but also easy to connect back up if you take it apart. So here's the first board. From the look of it, you can tell that this was made in 1985. There is absolutely no surface mount components on this board at all, but a lot of analog processing, entire analog processing section here. And you can see there are several mistakes. All these wires that are on top of the chip, they're not supposed to be done that way. But overall, if you ignore that, it's a really beautiful design. Everything is really carefully laid out. All the components are very nicely soldered. If you look at the other side, you can see very clean soldering. You can see a bunch of other mistakes. Here's the resistor there and a resistor there, but very nice. There's a little bit of flux left on the board from somebody who has done some repair, or let me see what is on that side. It's just a diode there. So there's a little bit of flux left on it, so I'm going to clean that up. I'm a little bit hesitant to clean something even because it may affect the calibration, because that flux does something to the board, and that might be part of the calibration. They may have calibrated it out, so maybe it's better if I just leave it alone. So here's one of the boards. Let's put it aside. The second board, I believe, is a PLL board, which generates all the signals for the chopper and any type of frequency measurements. If I can get it out of there. Here we go. Here's another one again. Lots of mistakes, but it's funny because someone has actually gone and made a little knot with some kind of string there to hold these cables in place. So even though it's a a botched job, it is done even with grace. This instrument is made in Japan, so they've taken good care even to fix their mistakes in a nice way. So you can see some more mistakes back here with the cables. But again, very nice. Everything is a nice grid here, nice thick power lines, nice gold plated connectors, and everything through hole. No surface mount components whatsoever. And the last board is a digital board. Let's see if I have to remove that. Yep, there we go. This is a GPIB connector. Can pull this one back out. So all the digital processing is done here. The firmware chip is in here. So you can see there's a battery to hold all the data in the memory, calibration data, or settings and user settings. There is a electronic erasable, ultraviolet erasable memory here, which is probably the firmware settings. It's covered up, and there's some numbers and dates written on it. It says probably version 002 or something. You can see a bunch of digital blocks there. Again, a few other mistakes. There's a little knob up here that you can, it says underneath it cal switch. So I think you can switch different calibration settings into it. I haven't read the manual to know. And they have a nice shield here to prevent either any shorts or just to separate the sensitive PLL from this digital block. So we put this back. So we can look at the bottom of the motherboard. There we go, nicely done. 3 connectors, again with the wall separating the sensitive. So all the analog processing is done in this bay. So there's a wall there that separates it, so there's no noise injected into it. All the wires that I disconnected are sitting there. You can see there is 2 LEDs at the bottom for the plus and minus power supply. The fuses are there. Not the best place to have the fuses, but the fuses shouldn't fail. Anyway, so there's a nice filter on the VDD line, which is sitting right down there where you plug in. This is where the plug is, if I'm not mistaken. Yes, and there's some AC filter module back down there. The power supply is in here. So overall, a very nice construction, clearly all done by hand. All of these wires and wrappers and all this, everything is somebody has done this manually. All the free optic electronics, of course, is done by hand. So let's close this up again and see if we can do some measurements with it. Okay, I put the cards back in, so let's just take another look at its operation before I close it back up. You can see the mirror moving back and forth. The input where the fiber comes in through the back. The detector board, the sensors, on the right side here the deep infrared, the regular sensors and the visible at the bottom. You can see it in glass, the one down there. The mirror here, which can switch between upper and lower infrared bands. Oops, I blocked it again. So there you go. It's not. It just recalibrated itself. The moving mirror. Let me see if we can get a shot of the inside of the mirror. You can see the reflections. And here's the other mirror. Close look at the prism, where the light is split into 2 paths. This is where the cards sit. You can see the 2 lights are on, showing the power supplies are functioning. The ribbon cable that goes to the GPIB, the high voltage, that's the switch, that's the main switch, the high voltage board. Power supply at the back, the stepper motor driver, and the stepper motor itself. So, you see also a look in the front of the unit. You can see right now it's on. It says 0 because there is no light present. There we go. So let me close it up because we cannot do a measurement while it's open. The stray light will interfere with the detectors. So to test the wavelength meter, I'm going to use this laser module. Now inside this little package is more than just the laser diode itself. There is also a modulator, there's temperature control loops, there is even a cooler, a solid state cooler that's built into here. It measures the wavelength, approximates the wavelength that comes out, as well as the optical power that comes out. All of that is necessary because the laser's center frequency or its wavelength is a strong function of temperature, and it has to be very carefully controlled in a feedback loop in order for you to have a stable laser source. But for this purpose, I'm only connecting to the laser itself and leaving all the other pins unconnected just to get a source of light coming out of it. Once I have some light coming out, then we can measure the exact wavelength. But I'm going to underbias the laser significantly because I don't have any of the loops active. I don't want the module to get into a thermal runaway. But we are going to heat the module up a little bit so we can see the wavelength shift. Now, the instrument itself has a FC type fiber connector, which is not the same as what comes with this laser module itself. So I have a piece of fiber here, and that fiber converts from the one connector to the FC type. So I'm going to take the FC type's cap off and remove the cap from the instrument and connect this fiber to it. There we go. So now we have the same type connector on this end. And you can see that from the module I have a piece of fiber coming out. So I will take the connector off of this end, connect it into this converter here that allows me to connect two of these fiber connectors together, such as this. There we go. So now we have a direct connection to the instrument. And in order to turn this guy on, I'm going to use my power supply. Usually you need to be very careful powering lasers because you have to use a precision current source because you're dealing with a diode. But in my case, since I'm under biasing it, I'm just going to apply half the forward bias voltage, and it should provide sufficient light coming out for the instrument to measure it. So here we go. Set the power supply, turn it on. So 1 volt, and it's taking 30 milliamps. And the light that is coming out of the fiber, which I definitely don't recommend you look into because it's infrared, you can't see it. It's around 1,550 nanometer, based on it, according to the data sheet. So if I look at the data sheet, it says that the wavelength should be at room temperature somewhere between 1530 to 1563 nanometer. So let's turn the laser off. Go to the instrument. Here we go. Turn it on. Let it power up. Do a startup calibration. Okay, it succeeded. The calibration went through. So since I know the wavelength is above 1000, I select the 1 to 1.6 micrometer. So you can see it gives me a whole bunch of digits. Right now it says 0. So I'm going to turn on the laser. There we go. And there it is. It's measuring the wavelength coming out of the laser at 1.545 micrometers. So 1545 nanometer, which is right in the middle of the range that I believe I said before. So it seems to be working really nicely, and you can see that right now, because I'm only putting 30 milliamp at 1 volt, which is 30 millivolts, 30 milliwatt of power in it, so it's going to take a long time before it really heats up. But the wavelength will drift, so I'm going to wait a minute until it kind of stabilizes in temperature. Then we're going to take a relative measurement, and I'm going to heat it up with a soldering iron and see that the wavelength shift. Okay, so I waited a little bit. Now the wavelength seems to be fairly stable. So what I'm going to do is I'm going to make a relative measurement. So this instrument allows me to measure deviation from, or a drift from, a specific wavelength. So if I'm going to press this guy, and I'm going to press this, now it's measuring the drift. So this is now in nanometers, so you can see that it's essentially not drifting at all. So I have my soldering iron here, set to about 600 degrees Fahrenheit. So I'm going to touch the body to heat up just a little bit so you can see the drift in wavelength. Here you go. I'm about to, so just to show you what exactly I'm doing, I'm just going to touch the side of the body of the module. Since it's all metallic, the temperature of the entire module will go up. So here we go. There you go. I've made contact with it. Give it a little time. You can see now the wavelength is beginning to drift away. There you go. It's already 200 picometers away from where it used to be. It's going to continue to rise. Now it's about half a nanometer away. If I keep heating it up, is going to continue to drift away. So this demonstrates the importance of having a temperature stable laser, otherwise you're just going to go all over the place as soon as you try to establish a link. So we don't have to look at it in wavelength, we can actually look at it in frequency. So this is the frequency deviation. There it is, that's in gigahertz. So if I'm not mistaken, 0.0249 terahertz is already shifted away, and it's going to continue to drift as I heat it up more. So I'm going to go back to measuring. I want to get out of this frequency. There we go. So now it's continuing to measure again. It reset the drift. So if I go back to measuring if I turn the drift off, you can see the original wavelength again. So now I'm going to heat it up a little bit more, and then I'm going to remove the heat. You can see it's going to drift back to where it used to be. So I'm going to heat it up a little bit more. There we go. It's not sufficiently warm, so I'm going to turn the drift back on. So now it's cooling back, reaching back to ambient temperature. So I put this back, and you can see that the wavelength is going to shift back to where it used to be. There it is. It's going back, slowly going back in the right direction. So the module is now quite warm. So, well, I hope you liked the teardown of this instrument. I really enjoyed looking inside and investigating the operation. Even though I had heard about how these things work and I read about it, it's a completely different story when you take something apart and see it physically do what it's supposed to do. So I had another entire video planned for today. Unfortunately, didn't get enough time, but there's an interesting, exciting video that I'm going to reserve for next week that has some cool experiments in it. So tune back next week. Hopefully, it will be up.